Hello everyone, my name is Chongwon. In this project, I implemented a ray tracing program that renders a single sphere with a texture applied. My contribution focused on rendering a sphere with a UV mapped texture, including the implementation of ray sphere intersections. The output is a static image. The sphere used UV mapped coordinates to wrap the texture correctly. Here you can see the result image, where the texture appears smoothly across the surface of the sphere. The program reads the texture from a PNG file, calculates the color for each pixel based on ray sphere intersections, and writes the final image to output PNG. First, I parse the object file to create a scene object. This allows me to store all bar size UV coordinates and paste from the object file in an organized way. I then create a new sphere object to add a simple geometry primitive to the scene. I set its center at the origin 0, 0, 0, which simplifies the ray sphere intersection math because the sphere is centered at 0. I assign it a radius of 1 so the sphere has a known unit size. Finally, I add this sphere to the scene's list of spheres. This ensures that during rendering, the ray tracer will consider this sphere for intersections. For each sphere, I calculate the vector L from the ray origin to the sphere center. This vector represents the relative position between the ray and the sphere. I compute A, B, and C, which are the coefficients of the quadratic equation derived from substituting the ray equation into the sphere equation. The discriminant tells us if the ray intersects the sphere. A positive discriminant means there are real solutions, that is, the ray hits the sphere. If the discriminant is positive, I calculate t, which represents the distance along the ray to the intersection point. I only consider positive t values because negative t would be behind the camera. If this intersection is the closed one bound so far, I calculate the exact intersection point, P, using the ray equation and the surface normal n by subtracting the sphere center from P and normalize it. Finally, I store this intersection and mark the corresponding sphere as closed sphere. Once a sphere is intersected, I calculate UV coordinates to map the 2D texture onto the 3D sphere. The horizontal coordinates U is determined using the a tan 2 function on the z and x components of the normal. This maps the angle around the y-axis to a 0, 1 range. The vertical coordinates v is calculated from the arcsine of the y components of the normal, mapping the height from bottom to top of the sphere to 0, 1. I then pass these UV coordinates to the sample texture function, which patches the correct pixel color from the texture image. This ensures the texture laps smoothly around the sphere according to its geometry.